Okay, so next talk is by Professor Stamp. So, Philip.
Okay, good. Thank you. Okay, so I'm going to talk about a specific theory which is supposed to go beyond the conventional theory of quantum gravity. So let me start, however, by mentioning that I've always been very fascinated by these two papers, as well as by the office which I was allowed to visit during a visit to the Lebedev Institute a few years ago. The thing that always intrigued me about these papers was that I was very familiar with the work of Fradkin, and I couldn't understand when I read the first one why there was apparently no influence of Fradkin and other colleagues of Sakharov in this paper. But then later on, I discovered the second paper and understood that, in fact, there was an influence. Anyway, you'll see when I'm in some of the discussion of this theory that I'm going to tell you about, that there is actually a definite influence of the work of Fradkin in it. Okay, so let me move on. So I'm going to talk about a theory which started some time ago, actually in 2012. Can you see my cursor?
Yes.
Oh, good. Okay, thank you. And has been developed since then in collaboration with a number of other people. I should like to specifically mention Andrei Barvinsky, who joined in the effort maybe, oh gosh, now 3 years ago or more. And also my students, Colby Delisle and Jordan Jero Wilson. Jordan in particular has been working on this. And also collaboration with Yanbei Chen in Caltech. So as you can see, there's quite a lot of papers now, and I'm not going to obviously talk about all of this. I'm going to try and give a short explanation of what's going on here. So let me start off with the intuitive idea, just so that people know what's going on. This, I guess, was an idea I'd been thinking about for a long time, and it was really Joe Polchinski in Santa Barbara who twisted my arm quite hard, actually, to make me publish it. And so that's why the thing started in 2012, because I'd had a discussion with him during a visit to Santa Barbara in 2011 about this. So I was very familiar, and I'll say a little more about this, with old work of Kibble, who had been trying to modify quantum mechanics to make it into a nonlinear theory by incorporating general relativity as a mechanism for causing, in fact, the breakdown of the superposition principle. And I'll say a little bit more, as I said, about what Kibble tried to do. But the key idea here is that you have correlations between matter paths, as well as between paths for gravity. Probably I should call these histories in line with what Jim Hartle says, because we're not actually, except for the particles, talking about paths. And the idea is that there is a kind of a universal mechanism which causes the breakdown of the superposition principle here, which comes from gravity. Gravity is rather unique. It only sees the stress energy tensor, and therefore it can't distinguish between n paths for a set of n particles from a set of n paths for the same particle. And this plus the equivalence principle, as we'll see, leads to a unique form for the theory that I'm going to discuss with you. So I'm showing you how one thinks about this in terms of paths at the bottom here. On the left-hand side, I have the conventional theory. So I'm showing you two different paths, paths A and B, for some particle in quantum mechanics. And let's imagine that this particle is also interacting with, say, the gravitational field. And we see that there are two independent paths here which have to be summed, a la Feynman, in order to get the final amplitude to go from 1 to 2. And this is a crucial point in quantum mechanics. It's called the superposition principle, is that you sum over these independent paths. So in the theory that I'm going to be explaining, that is no longer true. There are, in fact, correlations between the paths, but they're mediated only by gravity. There is, of course, no other communication between these paths by any other field except for gravity. Otherwise, everything is treated quantum mechanically in the sense that we exponentiate an action divided by h bar to calculate the contribution of each path, and all of the fields are treated in that way. Okay, so that's the intuitive idea here. So let me give some prehistory. Well, first, there are two elements to this history, at least as far as I'm concerned. The first comes from the gravitational side. As was already explained by Marcus in his talk, Feynman first raised the possibility that quantum mechanics might fail because of gravity, and he suggested that one should be focusing on phenomena in which one was dealing with masses whose mass was of order the Planck mass. As I already mentioned Kibble. Now, what Kibble tried to do was reformulate everything with a nonlinearity arising in quantum mechanics because of gravity. But he did this within a conventional quantum mechanical framework of Hilbert space and states and operators and so on. And he was, in fact, talking about states of the kind that we see at left here, in which you have a superposition of two branches, if you like, of the wave function, in which both the matter state and the gravitational metric are involved in the superposition. Now, Kibble decided, in fact, that he'd failed, and in fact, he decided that the reason he'd failed was because that it simply didn't work if you tried to force fit a new kind of theory of this kind into the conventional framework of Hilbert space, operator, measurement, and so forth. And in fact, he wrote a paper in which he tried to modify quantum mechanics, in fact, reformulate it without any notion of Hilbert space. A very interesting paper. It's actually this paper here, the Communications and Mathematical Physics, volume 65. But at this point, he actually gave up, except he did, in fact, discuss the kind of experiment that Feynman had already been mentioning and analyze it semi-classically. More recently, Roger Penrose also had a go at this and was also looking at the interaction between two paths. Well, actually, he doesn't frame it in terms of paths. He just imagines two states in the same way that we're looking at with Kibble. But he argued that there should be some sort of interaction between these states, which would be gravitational. Now, I was actually only aware of the Kibble work when I first discussed this with Joe Polchinski and explained why I thought that it was pointless trying to do it in terms of ordinary quantum mechanical notations, but that if you used paths, you could actually put together a consistent theory. Later on, I met Roger Penrose, who made it quite clear to me that as far as he was concerned, there was no theory. There were only arguments, dimensional arguments, such as the one that he made. So I thought that it would be interesting to write down a theory. But there was another consideration in my mind here, and this came from condensed matter physics. It was suggested a long time ago by Tony Leggett that one should try and do experiments in which one looked for a breakdown of quantum mechanics for large systems. And he specifically suggested experiments on superconducting quantum interference devices, SQUIDs. Now, those experiments were done, giving you some results here, but I think that, in my opinion, the work of Birgitta Worley at Berkeley and collaborators has shown quite conclusively that the experiments did not demonstrate macroscopic coherence, that the superpositions involved were actually rather small. She actually calculated with her collaborators, essentially, if you like, the number, the level, if you like, of entanglement that was involved here. There's nobody who's ever produced a good name for this number. It's sometimes called macroscopicity, sometimes it was called disconnectivity. In any case, you see that these numbers are pretty small. We're talking about just a few hundred or a few thousand particles. As Marcus mentioned, similar experiments have been done. Well, sorry, let me first of all mention that there are also experiments which show entanglement of spins, but the same number emerges, 10 to the 2 or 10 to the 3. And in the mass interference experiments that were mentioned by Marcus in his talk, well, actually, it turns out that my number here is too large. It's actually 24,000 AMU. That was what Marcus told us. This last experiment here, the one involving the superpositions of masses in two different places, is the only one that actually involves mass displacement and therefore is connected with gravity. And you see that we're very, very far from having shown that quantum mechanics is valid at the macroscopic scale in this sense. In other words, extrapolations of quantum mechanics to even objects the size of the Planck mass, let alone to the size of the universe, are unsupported by any experiment. So let me now explain the formal structure of the theory, which I gave you an intuitive picture of at the beginning. So in conventional quantum gravity, let's imagine we're dealing, just for simplicity, with a scalar field, which has an action, which I'm showing here. We'll assume that gravity is frozen in some metric g. And so then you just have the conventional sum over all histories, if you like, for the scalar field in that background metric g. Now, in conventional quantum gravity, you then functionally integrate this over different configurations of g. And there's, of course, a whole bunch of gauge fixing and Fadeev-Popov factors involved in doing this properly. But one can think about this in terms of, these are genuine closed path integrals, so a little bit different from what Neil Turok was talking about yesterday, but one can write down something of this kind. And you see here that with these closed scalar field paths, one is producing interactions between different parts of the path mediated by gravity. So what's different in the CWL theory, which by the way means correlated worldline theory? Well, it took a while to get the form that I'm showing you here. In fact, a crucial insight was provided by Andrei Barvinsky back in 2018. But here we see that we're basically what we're trying to do here is look at all possible interactions between an arbitrary number of matter paths mediated by gravity. So the index little n here is the number of paths being considered. And then if I then look at this q sub nj, it's in here, you see that it's just like what you have in conventional quantum gravity, except now we've, as it were, multiplied the number of gravitational fields as well as the number of matter fields. Andrei likes to call these replicas, which is something that I strongly object to. These are paths for a single particle. We then take the limit as little n goes to infinity, and then we in this formulation, so you can see here I've done this diagrammatically. This is the first. This is just for a single set of paths. This is for a pair of paths, a triplet of paths, and so forth. And you see that there are gravitational interactions between these. And then we take this to an exponent, which is alpha sub n, which is essentially bringing this back to what you would have for a single system. So we actually did a lot of work. This is mostly myself and Andrei Barvinsky, looking to see if this theory was consistent, because it's well known that whenever one tries to generalize beyond a conventional quantum field theoretical framework, you very rapidly arrive at inconsistencies. But we were able to show that all of the Ward identities that one would expect for this theory, diffeomorphism and others, were obeyed, that there was a sensible classical limit, and that there were also sensible expansions, both in powers of h bar and of the gravitational coupling for this theory. And I'm not going to discuss all of that. It's in the published papers, and of course it's fairly technical. But it was interesting to then see what you got when you tried to calculate the propagation of matter. So again, if we do this in conventional quantum gravity, then here I'm imagining that we're propagating a scalar field between two space-like surfaces, as well as propagating the gravitational field. So these are the induced metrices on these two surfaces. And this is essentially what this is at least one way of formulating conventional quantum gravity. So then the question is, and this, by the way, is supposed to be simply a propagator for the matter field and for the gravitational metric between these two. And actually some of this was already discussed by Neil in his talk yesterday. Now he was very worried about how exactly one treats these functional integrals. And let me say immediately that we do not, in this theory, make an imaginary time substitution. We always work with e to the is when doing calculations. In the CWL theory, you get the same sort of structure as we saw for the generating functional. So we, as it were, produce, we go to a large number of paths, have the interactions there, and then take this route to get a formula which is similar to what we saw for the generating functional. Let's see what it looks like in diagrams. So I'm looking here at a set of 3 matter paths for the generating functional. Now, I would have liked to have talked about this with when we were talking with Neil yesterday, but the point is that you can define the propagators by essentially making cuts through this generating functional. And we then see that we have 3 matter paths here, which are coupled to each other through gravity. And then if we want to define an initial and a final state for the matter field, we simply tie together these lines for that initial and final state. And again, one can do consistency analyses here, but the point is that this is a way of defining propagation of the, for example, of the matter field between these 2 hypersurfaces. Okay, one can do perturbation expansions and powers of the gravitational coupling here. One can also do semi-classical expansions around the classical limit, which is in fact general relativity. So what I'm going to do now is show you a little bit about what happens when you do these expansions. So first of all, I'm going to discuss a few non-perturbative results in this theory. There are interesting diagrammatic rules, which I don't have time to go through, but what you find in the CWL theory is that all good diagrams involving, in which you have loops in which there is a graviton, disappear. Now, this immediately smacks of the old analyses, amongst others by Jim Hartle and Gary Horowitz, of large N gravity. And in fact, there are certain interesting similarities between large N gravity and this theory. So when you throw away all these graviton loop contributions, you then find that it's actually possible to get an exact result, which is also found just by doing an Eikenau expansion around the classical limit. I haven't yet explained the classical limit, but in fact, we then find that the generating function can be written exactly for the system as an exponential of an exponent which has both the Einstein action here around the classical metric plus a term which is connected with matter. And one then finds that the saddle point solution for this is simply the Einstein equation that which you see here. Now, this equation is valid both for large and small masses in this theory. The metric field, if you like, is behaving a la Einstein here, both for large and small, for weak and strong fields. Okay. Well, the next thing one can do is look at the propagator for matter. And again, you find that one can derive an exact result. And again, you find that all of the graviton loop contributions disappear. And now one finds a result for the propagator of the matter field, which again involves an exponent, but now it's, again, you see the gravitational action here and a contribution from the matter field. This gravitational action here, however, is if you like, it's a restricted action in the sense that you've specified that the matter field starts in state phi 1, ends in state phi 2, and that the gravitational field is also fixed by induced matrices on the initial and final surfaces. The psi 0 here is nothing but the action of the matter field. Sorry, it's the propagator of the matter field in a specific background G, which we then find is actually the classical field. So at first you think, oh, all we've done here is rederive semi-classical gravity. Turns out that's not correct, because each of the paths here propagates in the field generated by the other paths. And so for small masses, we simply get back conventional mechanics in which we sum over the different paths. We just get conventional quantum mechanics, which is a sum over matter paths. So the interesting question then is, what happens when the mass of the object increases? Well, from a diagrammatic point of view, it's actually very simple to see what happens. So let me point out that at lowest order, graphs that you would expect to see in a perturbation expansion, actually not there. So for example, this top graph here, which is simply the lowest order contribution to the self-energy involving, in fact, a radiation reaction term, is not there, nor is this tadpole term. But so in other words, the form of the theory of quantum gravity for small masses does not look like conventional quantum gravity. But if I increase the mass, it will see that the matter lines collapse onto each other because of the attractive force of gravity. And so this graph here, which is the only one that survives at lowest order perturbation theory, involving an interaction between pairs of paths through gravity, collapses to look like the conventional graph, the conventional self-energy graph, because the two paths are forced onto each other. And I've shown here other examples of how the coupling between triplets of paths by gravity, when you have a large mass, collapses onto one path with conventional looking results. And in fact, you can show that for large masses, you just get back the standard perturbative expansions that are used in classical gravitational theory to, for example, calculate in spirals of black holes and so forth, perturbation expansions. Okay, so let's look now at lowest order perturbation theory in the gravitational coupling. So if I do that, you would think that there would be 4 graphs here, but as I've already described, this graph, and this graph all have graviton loops, and so they give 0 contribution, and the only one left is this one. This graph describes the propagation of a particle, say, in which 2 paths are correlated by gravity. So one can rapidly derive an expression for the propagator up to second order perturbation theory in this language. And the point is that you have functional integration over the pairs of paths here. This is for a scalar field, so phi and phi prime. The contributions from the actions of each path, but then there's this function here which correlates the path. This is what we call the CWL contribution to the exponent. And this is just given by the interaction between the stress energies for each path mediated by a graviton. So then you see that there's a mechanism that comes into play immediately in this theory, in which a pair of paths for a given system, for a single particle, say, will actually be attracted towards each other. And this gives a phenomenon which we call path bunching. In other words, the attraction between a pair of paths for a single particle, and we're assuming here a particle which is moving in intergalactic space, will nevertheless, these paths will be attracted to each other. So we do not expect the standard wave packet spreading that you have in conventional quantum mechanics to occur. And in fact, in the non-relativistic limit, in other words, in the limit where the particle is moving slowly, this is simply the Newtonian interaction between the pair of paths. Okay. Well, it's pretty obvious that if the mass of the particle is really small, the effect of this will be negligible. And I'll show you in a minute just how negligible it can be for a single particle. In fact, I'll do this now. So we see here that there's this effective interaction. This is the Newtonian attractive potential between a pair of paths for our system. So we see that, that there are a number of key scales here. One of them is the, if you like, the analog of the Bohr radius for this Newtonian attraction. So that analog here is proportional to 1 over the mass cubed. So this is the Planck mass, this is the mass of the particle, and this is the Planck length. Let's have a look at what that length scale does for a particle with a given mass. So if the mass of the particle is that of the electron, then this length scale is roughly 6 million Hubble lengths. So it's very, very large for an electron. The other key scale is what is, if you like, the analog of the Bohr binding energy for the pair of paths. This is shown on the right-hand side. And we see that for an electron mass, that actually is, it's about 10 to the minus 86 electron volts. So you can see that the effects of this pair or this path bunching mechanism for an electron are absolutely negligible. So when do they start to become important? Well, we see that this binding energy comes up to roughly an electron volt when the mass of the particle is of order 10 to the 13 atomic mass units, which is about 5 orders of magnitude less than the Planck mass. And the corresponding length scale has collapsed right down. You notice that this binding energy goes like the 5th power of the mass, and the length scale goes like 1 over the cube of the mass. So they vary extremely rapidly with the mass. Now, the problem with this sort of hand-waving discussion here, well, there are two. One is that it's a perturbation result, and the other is that I'm doing it for a point particle. Well, we can easily deal with the fact that real masses are not point particles, particularly when they're as big as 10 to the 13 atomic mass units. So we redo everything for an extended mass. And the results here are kind of interesting. And I'm not going to go through all the technical discussion. This is just here for anyone who wants to look. It's actually rather important to know whether or not the system is crystalline or amorphous. The results depend a lot on material parameters like the phonon spectrum. But the general result is shown at the bottom here. Instead of the, and this remember is still in second order perturbation theory, this calculation, but instead of the 1 over r attraction, we see that it bottoms out and becomes essentially a harmonic oscillator well here. I'll explain these spikes in a minute. And the key is that the frequency of oscillation in this well turns out to be independent for these large objects of the mass. In fact, it depends only on the material properties. So for example, if this mass was made of gold, it turns out that the oscillation frequency in here would be roughly the oscillation time period would be roughly 1,000,000 seconds. In other words, 2 weeks. Now, these spikes here come from the fact that if the two paths are displaced by a crystal lattice spacing in a lattice and exactly along the lattice vectors of a crystal, then an ion, or rather the nucleus of an ion, will overlap with an adjacent nucleus for the other path. And so you get this very sharp attraction. The reason it's smoothed out is, of course, because of phonons. For an amorphous system, or for any situation where the paths are not displaced along a lattice vector, all of these spikes disappear except for the central one. And the central one is basically for paths that are very close to each other. And in that case, the oscillation timescale is more like 16 seconds. Now, these are long times, these oscillation times. It means that if you're going to look for deviations from conventional theory, you're going to have to look at this sort of time scale. Bill pointed out to us some time ago that we ought to be worrying about whether or not LIGO had already falsified this theory. But it turns out that, first of all, the frequencies are way off by a factor of about 10 to the 4. And secondly, there's another problem, which I'll now discuss. Oh, sorry, I'll discuss it in a minute. I beg your pardon. I'll come back to that. It's very interesting to understand what this theory means to just look at an ordinary 2-slit experiment of the kind that Marcus was describing, and of course, of the kind that Feynman first discussed. So I'm simply amplifying on what I said before, which is that in this theory, it's harder for paths for a massive particle to separate from each other because of this attraction. Each path is moving in the metric field generated by the pair of paths. And so if the attraction between these is very strong, then we'll essentially see collapse onto one or the other of these trajectories. Now, as I said before, for small masses, this is irrelevant. We have to get up to masses of order 10 to the minus 5 Planck masses at least. But for a large mass, we'll see effects of the kind that I discussed on this slide. We'll see, in fact, there'll be an attractive potential binding these paths, whose length scale is of order the size of the mass and whose characteristic oscillation frequency is of order 16 seconds. There is a problem here, however. In order for the path bunching to actually happen, because this is a dynamic process, we need to get rid of the, if you like, energy. So if you imagine two paths starting off far from each other, for them to collapse down to each other, in other words, to fall into the bottom of this potential well, we have to get rid of the energy, which is in fact stored in the interaction between the paths. And this is where we arrive at a problem with experiments, which is that most of these experiments are designed so that there's very, very little dissipation, which means that the time scale for the collapse of the paths onto each other is actually rather long. It's actually the 16 seconds that I just told you about, multiplied roughly by the Q factor of the system. So we've discussed ways in which one could prepare the state of the system, collapsing the paths by dropping Q to a very low value before doing the experiment and then increasing it. I was going to discuss some of the proposed experiments, but Marcus already did. So I'll just pass over this slide here. He's already discussed pretty much all of this. So let me just summarize what's going on here. The first problem was to find a consistent theory in which quantum mechanics breaks down and the mechanism is gravitational. So the CWL theory is such a theory, and we've shown that it's actually consistent internally. That is to say, it's consistent with all of the theoretical tests that one can devise. That, of course, doesn't mean it's consistent with experiment, but one has to then explore the theory to produce experimental predictions. Notice that there are no adjustable parameters in this theory, that for large masses, it reduces to classical general relativity, and for small masses, it reduces to quantum mechanics. So it's a theory which, in fact, contains both of these. There is a breakdown of quantum mechanics, which starts to show itself for masses of order 10 to the minus 5 Planck masses. But the problem in testing the theory will come because path bunching is actually a rather slow process. And Marcus already discussed experimental tests. Let me just briefly mention work that's going on right now. The first is work on the effect of conventional dissipation and decoherence mechanisms here. And there are two reasons for that. One is that, as I just explained, these mechanisms actually control the dynamics of path bunching. But it's also, if you want to do experimental tests, then as Marcus made very clear, we want to get rid of decoherence, at least when we're doing the experiment. And this is work that I'm doing partially with Birgitta Worley from Berkeley. And in that connection, let me mention that I think it's actually not quite true that we don't understand these decoherence mechanisms. There's actually very good experimental demonstration of the theory for decoherence from photons and from phonons and magnons and so forth. And this has been done in cavities, it's been done in spin systems, superconductors, semiconductors, and insulators. The problems arise because a lot of the decoherence and dissipation at low temperatures actually comes from defects in almost any solid system. And this is harder to understand because we don't have a decent theory of defects. There are also problems because one has indirect decoherence mechanisms, what Bill and I once called third-party decoherence. And there are also long-range decoherence mechanisms. So this is a problem. We need to understand this a lot better. And with Yanbei Chen at Caltech, we've been designing all sorts of experiments, which we'll be very shortly publishing. But there are also other things, because you notice that this theory involves general relativity in a very crucial way. And it makes you wonder what happens when, for example, there are achronal regions, or one worries about retrocausality. And this is also a topic which Yanbei and I have been discussing for the last 3 years without a clear resolution yet. And so that's, if you like, coming. And then finally, of course, one would like to understand how to discuss conventional quantum measurements. You notice that there is no requirement in this theory for a special place for measurement, because the crossover to classical physics occurs for large masses. In other words, we don't have to introduce some separation between the classical and quantum world. It's generated already in the theory. but one would still like to know how to describe many of the standard measurement systems. So that's basically all I wanted to say. I just want to thank my collaborators here, particularly, as I said, Andrei Barvinsky and Jordan and Yanbei. And then over the years, I've had a lot of very helpful input from all sorts of people, starting with Marcus, who is here at this conference. And well, I won't bother to read them all out. So thanks very much.
Thank you, Philip. I see first question is by Jim Hartle.
Hi, I wanted to ask, with this theory of quantum gravity, how do you do cosmology? Do you propagate from the Big Bang?
Right. So every time I'm asked that question, my answer is usually to say, look, we've got to make sure this thing works in the lab before we start talking about the universe. So I've had a lot of
that's a perfectly good answer. Later.
Right.
What you're saying.
However, I have to tell you, I've had a lot of discussions with Alexei Kitaev about this, starting in 2019.
Kitaev, is that what you're saying?
Yeah, Alexei Kitaev. Yeah. So the point is, I spend a lot of my time at Caltech these days. Well, I haven't so much recently because of COVID, but otherwise I do. And he and I have had.
How come you don't come out and visit us if you spend time at Caltech?
Well, I will. Just send the word. And Alexei had this idea, which I thought was really cute, which is that you could understand dark matter in this theory. We haven't actually had a chance to look at that. But the idea is that, of course, that there is energy, if you like, stored in the interaction between the paths, which is completely invisible in conventional terms. But of course, will have effects because it generates a gravitational field on its own. I have really not been able to work that out. But I mean, clearly, there are all sorts of interesting things one could do in this framework at the cosmological scale. And that's all I can say.
Big Bang, how is it represented in terms of the paths?
I just.
Oh, I see. It's later. Excuse me. You already answered.
This is question C.
C. Oh, global questions. Okay.
Yeah. So, I mean, my feeling is that, one thing at a time, basically.
That's fine.
Yeah.
Okay. The next question is by Sergey Shibirikov.
So, yeah, so my question is quite simple, but perhaps it's also inspired by this application to cosmology. So you will be talking in terms of masses, but what about quantum fields? I mean, what is the characteristic, like in terms of mass, you have transition from quantum to classical at certain masses. So now if I consider extended fields, and in cosmology, that's relevant for primordial fluctuations, for example, where we also treat like perturbations of inflaton as quantum field first, but then it goes into classical, objects. So what will change from the viewpoint of your theory in this context?
I think that somebody once asked Marilyn Monroe, what she was going to be doing in her next film. And she said, let me finish this one first. My feeling is that, so obviously we've worked a whole bunch of stuff out for scalar fields, but I simply haven't had time to apply that to the kind of question that you're talking about, essentially cosmological or astrophysical. Mm-hmm. And my main focus right now is on experimental tests in the lab of this theory, because these can be controlled. And in fact, there's something that I should have mentioned, which is that the parameters that you can vary in the kinds of experiment that we're thinking about here allow one to discriminate between any kind of conventional dissipation or decoherence mechanism and what's going on here. That's the first thing. And the second thing is that there is no decoherence in this theory. So let me make it very clear. People like Roger Penrose have talked about some kind of intrinsic decoherence in nature coming from this, but there is no such thing in this theory. So we're simply talking about a change in the dynamics of ordinary masses at a scale above roughly 10⁻⁵ Planck masses. And this is something that one can control in a lab very precisely. You can vary materials, you can vary amplitudes of oscillation, you can vary all sorts of things, which are simply not under the control of people who are investigating cosmological questions. So that's why I'm saying wait for the next film.
Yeah, yeah, thanks for this answer, but maybe putting it down in the lab environment. So can you, I mean, if I do experiments with the electromagnetic field in resonators, for example, instead of particles, what would be the
energy density?
Where the transfer, I mean, where your theory will
No,
develop?
that's a very good question. The problem is that right now the energy densities are too low.
I see. So that will be the energy density would be the parameter that controls.
Yeah, you would need energy densities here corresponding. Well, they'd just be absolutely enormous. I mean, so yeah.
I see. Thanks.
Okay, I see no other questions, so let's thank Professor Stamp once more.
Thank you.
Okay, and also thanks both of all speakers and all attendees. And we now is finishing our session.
So I'll take you up on that offer, Jim.
Where are we? Oh, Lee.
Yeah.
Thank you very much.